So we're going to talk about sarcasm, and we're actually going to talk about building a multimodal model to detect sarcasm. So NLP and facial expressions. So this is going to be a very, like I said, practical introduction into like breaking a problem down and actually building the machine learning models, and then doing like literally doing multimodal analysis. So my name is David Von Thenen. I'm an AI ML engineer. I've been in the space for some time. BC time, right? BC-wise, before ChatGPT was fully announced, right? So yeah, I've been in the space for some time. I tend to focus on NLP-related stuff, but I've got a bunch of other interests like vision, doing ML and AI on IoT edge, and then also building a, believe it or not, you can use machine learning to build out models to recognize disease for like medical models. Prior to that, I was in the Kubernetes and CNCF ecosystem, so doing open source Kubernetes contributions. And then prior to that, I was doing backup recovery solutions in virtualized environments, specifically VMware vSphere. So for the agenda today, we're going to talk about sarcasm. And what a difficult problem it is. And we're going to kind of then break the problem down. So I'm literally going to go through what does our data set look like? What can we do to fix it? We're going to start from an established research paper, and we're going to use their data set, and we're going to improve it, and we're going to improve on the techniques they use to get a better score on the inference. And so we're going to talk about the data set. We're going to talk about the visual cues. So how do we break down the facial expressions in order to help us, right, the video portion of how do we like detect sarcasm and how can we classify it? Then we're going to break down the audio characteristics, right? So we got vision and then we got audio. And how can we use the audio components in order to detect sarcasm? And then finally, in the end, we're going to take both of those two models, combine them together for our multimodal classification. This is technically a workshop, so I will have workshop materials for you at the end where you can try all of this at home. And then Q&A at the end, like I said. So sarcasm is tough. It's actually really tough, but humans actually have a pretty good understanding of it, and we can actually sense it pretty well most of the time. The interesting problem with sarcasm is that literally saying the same sentence or the same phrase just by changing your facial expression and intonation can have a drastically different meaning. So, example, great job. Great job, right? And why is this like really important in NLP? Because one is the complete opposite of the other, right? It's not great job, it's like what a horrible job, right? And the problem is if you're using text to analyze that, it looks exactly the same. And so that's why we need to start looking at facial patterns and intonation. So kind of to kick us off, some fun stuff. I have a video for you. It's actually from the Big Bang Theory Season 2, Episode 14. So let's go ahead and take a look.
Hey Penny, how was work?
Great. I hope I'm a waitress at the Cheesecake Factory for my whole life.
Was that sarcasm?
No.
Was that sarcasm?
Yes.
Was that sarcasm?
Stop
it!
So, right, sarcasm. It's, we kind of can see it. Obviously, we can see it. Sheldon has a problem with it, but it's a difficult problem, right? So, in a lot of the facial expressions and intonations, we need to take a look at to really kind of break the problem down. So, sarcasm fail. So let's go ahead and I'm going to do a lot of live demos. So we're going to take a look at doing sarcasm analysis using text only, using the most popular sarcasm classification model on Hugging Face. And so I've already pre-programmed 12 sentences. The sentences are actually really not important. And I'm just going to go ahead and run this. So Hugging Face predict. So 12 sentences, 6 of them are not sarcastic, and 6 of them are. So the top 6 sentences, it supposed to be not sarcastic, so normal sentences, but we're getting 2 that are coming back and being predicted as sarcastic. And then we have the bottom 6 sentences, which are supposed to be sarcastic, but we're getting a prediction back not sarcastic. Notice the high confidence scores. So this is the problem, right? You just can't rely on text alone in order to do your sarcasm classification. And by the way, these 12 sentences are actually some 12 sentences from the data set that we're going to use. So real world, like, trying to detect sarcasm, right? Oh. So now what? So what do we do? So how do we attack the problem? And so this is really kind of, let's break the problem down and try to figure out how we can actually do this. So the first thing we need to do, and like with all machine learning problems, AI problems, it always starts with the data set. And kind of like I said at the top of the session here, we're going to start with something that's already established. And the reason why is because there's actually a research paper. And not only is there a research paper, they actually have an open data set for sarcasm analysis, so sarcasm classification. It's called MUSTARD, so Multimodal Sarcasm Detection Data Set. And what they did was they actually collected a whole bunch of video clips from popular TV shows, 4 of them to be exact. Big Bang Theory, not a coincidence, I played that video. Friends, Golden Girls, and Sarcasm-aholics Anonymous. And so they also started with that data set in their research paper and in their, building out their models to classify sarcasm. They looked at facial expression, they looked at the acoustics, and they also looked at text. And they also wanted to, do this in a scientific way. So they did analysis for speaker-independent and speaker-dependent data sets. And we'll kind of jump into that actually in the next slide here. But if you're interested in the research paper, you can read more about it. The PDF's there. It's actually in the GitHub repo, on my repo with all the workshop material. So what is speaker-dependent classification? So if we're using the basically MP4s or video from these 4 popular TV shows, so speaker-dependent classification is where we take a mix of our data and we have like representation from Big Bang Theory, Friends, Golden Girls, and Sarcasm-aholics Anonymous in the training data, in the validation data, and in the test data, right? And so you can see now that when you're doing like the validation, right, the training for your model, it's using the same mannerisms and the same facial expressions from the data set that you're using to train the model. And when you're also doing the test, it's also using test data from those TV shows with those actors, with those mannerisms and all that information, right? So that's speaker-dependent classification. So independent speaker classification is, we're going to basically kind of divide out our data set such that when we actually go to test, none of our test data sits with our training or validation data. So training data, validation data, Big Bang Theory, Sarcasm-aholics Anonymous, the Golden Girls, train the model, then use all of the Friends videos to see if our model's actually any good or not. And so this workshop does both, right? So you can build the model for both of these 2 scenarios. So before we go ahead, like what were their results? What did they see? So in that speaker-dependent training, so right where you had the test data was also used in the training data, so right, the speaker crossover. So their best multimodal shot at it was using text and video, and that multimodal model combining text and video gave them a 72% accuracy rate, weighted F1. So independently, right, you have text, you have audio classification, and then you have facial expression classification. Text was 65% accuracy, speech was 65%, and facial was 67%. And so that's kind of independently, but we're more than the sum of our parts. You put 2 of them together, it ups your confidence when you try to do the classification. And in their case, text and video gave them a 72% increase in their accuracy rate, right? So for their independent training, so this is right, using new speaker information or data to actually run the test of validate if their model was any good or not. And so they combined text and audio, and they got a 63% accuracy rate, weighted F1. And in the individual models themselves, text was 60%, speech was 63%, and facial was 54%. And they actually even noted in their research paper saying that when they actually tried to introduce the facial classification into their machine learning, into their multimodal model, it actually negatively hurt their statistics for their, accuracy rate. So it was basically a coin flip would have been better, right, than actually using that model. So how can we improve that situation and make it better? So like most data scientists, it always starts with data grooming, and unfortunately it's a lot of it. And so we're going to clean up their data, and we're going to, I actually took the time and exercise of cleaning up every single video clip that they had to actually isolate what we're interested in. And so we want to visually isolate the speaker. We don't want to have other people in the background. We want to acoustically isolate the speaker. We want to remove dead audio and dead video. And then, as an additional enhancement, we're going to add other acoustic or prosodic features, so other audio features that we want to add in to the things that we can measure in terms of acoustics into this machine learning model that handles the audio portion. And then in the facial, right, how we measure their facial, and we do classification based on their facial expression as they're saying the sarcastic or non-sarcastic sentence. We're going to do a bucketing approach, and I'm going to go into these in a lot more detail in the audio section and then the facial section. And then we're going to do something called facial anchoring. And again, I'll kind of go through, and each one of these, I'll go through the data pipeline, I'll go through the architecture, and then we'll kind of go through results. And we'll actually run all these models live, so it'll be very fun. So what do I actually mean by video grooming? So like grooming data, right? So for facial landmarks, take note of this video. We're going to take a look at it and take note about what's happening.
Broadband. Leonard, may I present, live from New Delhi, Dr. and Mrs. V.M. Kutrapat.
So very short clip, right? Now let's take a look at what I did after for the grooming data, the video grooming.
Broadband. Leonard, may I present, live from New Delhi, Dr. and Mrs. V.M. Kutrapat.
So ignore the audio for right now. This is just the visual portion of it. But I isolated the facial expression for the person doing the talking. And you might have bleed through in some of the other facial expressions, right? Which is why you want to isolate the speaker who's actually saying this potentially sarcastic comment, right? Now on the audio side, let's go ahead and take a look at this.
I was going to ask Leonard to do it, but he seemed a bit emotionally unstable, and you don't want someone like that operating heavy machinery.
No.
So that's the before, right? Before I did the data grooming and cleaning up the clip. Now let's look or listen to the after.
I was going to ask Leonard to do it, but he seemed a bit emotionally unstable, and you don't want someone like that operating heavy machinery.
So what did you notice? So Penny said something, we actually missed it because of the, I guess, networking or whatever. She uttered something at the beginning, which got cut off, and I removed her saying something, that last little sentence at the end, right? Again, acoustically isolating the sentence. And so the original data set that they had those befores in as a part of their data set, right? So a bunch of grooming, data grooming is what I ended up doing. It took a fairly long time. So now we kind of understand what we did to fix the data. So now let's go ahead and break down the visual portion of it. So the facial, how are we actually going to measure the facial intent, the facial expressions on the actors' faces when they say what they're saying? So how do we do that? We need to measure, right? And so the best way of doing that is actually pulling data straight out of the video. And there's actually a cool library called dlib.net. And you can actually use that library, it's open source, and you can literally extract 68 points on a person's face. And they're actually outlined right here on the left-hand side, right? So everything from their nose, their eyebrows like moving up and down, their mouth as they're moving, their jawline. So we can record all of that information. And what that ends up looking like on the right-hand side, I guess it's the same for you as that is for me. On the right-hand side, you can see that, like how that maps on that person's face, right? So we have a way to pull information out of the video, right? And like measure facial expression. So some of the things that I ended up doing for feature engineering, right? If you can extract the information, what little hints can we do or add into the machine learning model to help it understand facial expression a little bit more? So some of the things that were added were like obviously position, right? So it gives you, so when you run that library and against a frame in a video, it will give you X, Y coordinates of every facial point in that frame of video. So you get the position and then acceleration, right? Because this is video, which is time-based. So over time, we can actually measure the acceleration, the velocity. Occasionally, if I'm turned a little bit this way, you might not see like this little dot right over here. So we had to interpolate and fill. So basically fill in the blanks when that stuff didn't exist. We're gonna do, fill in the missing landmarks, the missing points if they weren't captured. Handle variable length clips, right? If I cut some of these clips down, when you're doing machine learning, you need to use like for like comparison, right? So we're gonna do variable length, handle variable length video clips. And then the last one, nose tip anchoring, which I'll get into in the architecture portion, is actually very significant. And I'll get into more detail. So here's the original video.
You know, it occurs to me you could solve all your problems by obtaining more money.
Now if we use that dlib library, so I had to make those dots incredibly huge. Like when I superimposed it back on the video, if I kept it as just like a pixel, it is actually very difficult to see. So that kind of tells you about like the resolution of it. But I just had to make it big so visually you can see it in the video. So that's what we're gonna do. Frame by frame, pull out the 68 landmarks on the actor's face. So what does the actual data pipeline look like? Start with the video, go frame by frame, extract the 68 landmarks or the 68 points on a person's face, dump them frame by frame into a CSV file, and we're also gonna do, the velocity, acceleration, the buckets, the nose tip anchoring, which I still need to describe in the next thing, and LSTM to capture temporal dependencies, do some magic with parameter tuning and all that fun stuff, and out you have a model on the other side. So that's what the data pipeline looks like. So for the architecture, right? If you're not familiar with building machine learning models, this is a great introduction to like a lot of this stuff. So this is like one of the many things that you can do, long short-term memory, or LSTM. So if you ever hear that word, just think about time series data, right? How do I track measurements over time? And so that's what that kind of LSTM buys you, right? Because we're keeping track of facial expressions, like the eyebrows moving as someone's saying something over time. Now the buckets, which, I kind of already described, because I did cut some of the clips down into smaller ones because I had to remove other speakers who weren't contributing to the conversation. Now we have clips that are variable length. So what I did was I ended up taking grouped like-sized clips together, and the ones that were shorter in that bucket I just filled with zeros at the end to get it so that I can compare apples to apples, right? And for like the next group down and the next group down to the very shortest clip, right? Nose tip anchoring. Now this is super non-obvious. And it's probably why they kind of screwed up, like when they did the facial stuff. So if I have an actor's face and all of the points, X, Y coordinates in the upper, like right-hand corner, and in the next clip, right, machine learning training, in the next clip, I have the actor's face in the lower left-hand corner. The X, Y coordinates are completely different, right? So how do we fix that problem? So I kind of came up with this and I was like, oh, this actually kind of works. I used the nose as 0, 0, right? So all of the other measurements are relative to the nose. So that way, if the character's face happens to be in the upper right or in the lower left, it does not matter because we're using it relative to the nose. And so now I can actually make a pretty decent comparison when I train the machine learning model. So normalized coordinates is what basically that nose tip anchor means. The buckets to minimize the padding so I can compare like-to-like things. So, demo. How am I going on time? I think I'm good. Okay. So demo, let's see here. So I'm literally going to demo the extraction portion. So we have videos contained in data, Big Bang Theory, normal. I just put a few of them in there because otherwise it would take forever. And if we actually want to do the extraction, so we need to take the videos and we need to extract frame by frame. And thankfully, I created a cool shell script, which will actually do that. Now, if I actually go back to, I use sarcasm. Now you see a folder there, right? And if we actually look into that folder, you can literally now see that video broken down frame by frame. So now we have the video, every video, right, with the same folder name as the original video, broken down frame by frame. Now, how do we extract the facial features and put them into a CSV file? Turns out I created a little Python thing, application to do frames to CSV. So it's going to look into those subfolders, right, where it's broken down frame by frame. And sometimes there is no face, right, no points in a given frame. And if I look at that same folder, now we have a CSV file. So this is literally the data pipeline portion, right? And if we actually go back and look at the CSV file, first column's frame, second column's face ID, XY coordinates, jaw, nose, frame 2, so on and so forth, right? So this is our training data, validation data, test data. Now, to build the machine learning or the machine classifier for facial characteristics, you basically do Python, train best buckets, put the data in the data folder, which you see there, run that script, and it will train the machine learning model. We're not going to do that because it will take over 10 hours on an H100. So what we're going to do is we're just going to do the inference portion. So Python predict. So we have a whole bunch of videos, right? We've already done the training. The model is right here. And we're going to take the test data and we're going to say, hey, for every video now converted to a CSV file, what's the accuracy? And it turns out for the facial expressions is now 78.3% accurate, right? So F1 score, okay, even higher, great. So that's start to finish what the pipeline looks like and doing the inference for facial expressions. So Oops. Now, for the audio portion, you might say, like, how often does this actually happen in the real world? And it turns out quite frequently. And there's actually many ways of doing it too. So if you take a look at the picture on the right-hand side, upper right, that is actually a wave file, right, in pictorial form. X coordinate is time, and then the Y coordinate is frequency. So this is a wave file, represented as a picture. And it turns out that the picture right underneath it is every square is a pictorial version of a sound. And just visually you can see that there's certain patterns that start to emerge. And what the machine learning model does when you build it is it recognizes those patterns and says, oh, these two must be the same sound, same as that, right? And so that's kind of like the lo-fi version of building a classifier, right? And there's many examples of it doing cat versus dog, sound, environmental sounds, gunshot recognition. So it definitely is done. And so for the feature engineering part, right, we need to give hints to our machine learning model to say, hey, like what are some additional hints that I can give the audio classifier better, an increased chance at predicting whether this is sarcasm or not. So I added in a bunch of other things like RMS, so root mean squared energy, which captures projection, like when someone projects, like the energy of your voice, a harmonic to noise ratio, jitter, shimmer, a whole bunch of other things added in. So that's the feature engineering portion. So what does the data process, the data pipeline look like? So we have the video, we need to extract the audio, we then take all of the acoustic measurements that we can, send them to a CSV file, and then train our machine learning model using, right, because sound is, right, frequency over time, use LSTM, right, we need to track the acoustics over time. And I threw in something here which does transcription so that I can assign the acoustics to what is being said, the words that are actually being said. Tune the model, and then you have an ML model that as a classifier, right, based on audio. So what does the architecture then look like? So long short-term memory plus the convolutional neural network. So again, the LSTM stuff is how do I track measurements over time? So that's that time series data. Then doing the convolutional neural network is assigning the word to the acoustics of what is, like how that word is being said. And what I did was I took the audio clips, right now we're dealing with linear 16 wave files, and I just passed them through popular transcription engine that gives me word level timestamps. And which then now captures pacing, captures intonation, captures like the flavor of like how I'm saying the word. And then, so like, why is this effective? Long-term acoustics, I can kind of like track that now using the LSTM. Short-term linguistic acoustics, tie it to a word. And let's go ahead and take a look. So for the data pipeline portion, I forgot what I called it. Oh yeah, speech, okay. So same thing, I have videos, right? The MP4s, we need to extract the audio from them. I can never remember the commands, that's why I keep doing this. Now I don't have to remember. Now if I go ahead and so that script, that shell script basically took the MP4 and extracted linear 16 wave files. Oops. This one I guess I did normal. So, right, MP4 to wave. Now we need to take that wave file and we need to capture all of the things that we can measure, all the acoustic signature, and put them into a CSV file. So there's it's a Python script to do wave to features.csv. Now this one takes significantly longer. it's going to actually, hopefully doing this live, it's actually going to send it to, I'm using a transcription platform as a service to get the word level timestamps, and grabbing all of the acoustics, and you can see that we have that CSV file, right? I think it's normal. And this is what the CSV file looks like now. The JSON is actually the transcription with the word level timestamps. And then this is what the CSV file then looks like. So on the 5 millisecond border, I'm taking the acoustics at that granularity and then attaching the transcription, which is, the first word is since, the next word is it's, which maybe I can, right? It fell asleep, of course it did. Oh, there we go. So it's, so since, and then it's, and then so on and so forth. So now that we have all of the acoustics extracted, right, the acoustics and tied to a word, we can train the machine learning model, which you can do by just doing train with which words.py. This will take even longer on an H100, so we're not going to do it, and we'll just do the inference portion on a pre-built model right here. And for those that don't have access to an H100, so all of the models that I have here, they're in safe tensor format, and I've included them so you can download them so you're not like stuck having to train a model like on your MacBook or whatever. And the data sets, both in the original and then also in the cleaned up form, are all available on my GitHub. And if you don't want to do the data extraction, all of the CSV files, like after the fact that have been processed, are also there. So you can like literally jump into this at any point, however you want to. So if we do the inference, so the inference on the acoustics for this, we're just going to stop it right there. So this thing, using all of these test files to see like how good the model is, it's actually still going. It is 75, rounded up 76% accurate. It's actually still going. So I'm going to pause right there. Got any questions?
How are you dealing with frame rates?
I basically made everything the same. So for the video, because in order to, well, first the sampling of each frame is uniform across all of them. So I've extracted it that way, and also the audio, because the granularity, I've also extracted the audio in a uniform frame rate. And all of the audio is linear 16, 48,000 kilohertz, right?
Okay.
Yeah.
And like time code to the phrase, the audio?
Yes.
Okay.
Yep. And then the video likewise, because they're uniform time rates, or uniform time between each frame. We're grabbing that frame, grabbing the 68 point facial landmark points and putting them in that CSV file so that, yeah. Great question. Because if it was using different sampling rates between the frames or between the audio, it would throw everything off. Oh, yep.
So, great demos.
Well, we're still going. I'm just.
So far, like,
100%.
right?
And
So
you're
at that time, my nose is not visible. But
Yeah.
I'm still being sarcastic.
Ye-
So how do you work on that?
100%. So we're actually going to touch upon it in this section right here.
So you can
So the audio in that case would still be good, but the facial landmark obviously you wouldn't have it because the person's like looking away.
Okay.
So-
you'll still have a signature of the sarcasm through the voice signature, but not from the imaging signature.
Yeah, and in order to test, we need both.
Perfect.
Yep.
Oh,
So now we're going to take those individual machine learning models, put them together to do multimodal so that we can do the video and the audio, and we can classify and see like what our results are. So if we actually go ahead and we kind of, this is the summary of the speaker dependent, right? So we have the speaker crossover. Our test data also has comprised of all of the shows. The unimodal speech was 76% accurate. The facial one that we created was 78% accurate compared to the one in the original research paper. Speaker independent model was 69% accurate and 68% accurate on the facial portion of it compared to 63 and 54%. So now let's take those two models and put them together and let's do the multimodal classification. And so, oops. And this one, because we already have the two models that I have trained, right? They're just safe tensor checkpointed models. You can run them anywhere. We're just going to run the predict. And then there's different ways, right? Because each of the individual models has their own confidence score, right? How accurate, how confident am I in this answer? And there's different ways you can combine them. And I've actually gone through and I've done many different ways right here. But you can see that actually the majority of them are roughly 0.8, which is, did I not print it out? Well, I guess I didn't print it out. But it's, oh yeah, right here, sorry. So it's basically about 80% accurate. And like you were saying over here, in order to do that actual inference, I needed to have the pair. So the CSV file for the facial landmarks and the CSV file of the acoustics, pass them together, get a result for each one, do a combination of like the first case, the average probability, right? And it will give me a score of like whatever it's going to give me. So I think these are, yeah. So that's the multimodal part. Yeah. So what were the results of combining the two that we had built in this workshop? So that it's the speaker dependent was 80%, which is the one that we just ran like right now, was 80% accurate. The original research paper was 72%. The speaker independent, so new speaker at test time, was 70% accurate, which we didn't demo because I would have to demo everything twice. But I gave you all the code to actually, and like the organization of the data set so that you can actually build both of them. Was 70% accurate compared to the original 62%. So what could we improve even beyond what we've done here today? So future improvements. So this is literally, don't go taking this and like putting it into production. One, the data set was not large enough. This was more of like an academic research, like how can we actually do multimodal sarcasm analysis, classification. So if you had a much larger data set, give it a try. But like everything in machine and AI land, finding the data set's actually the most difficult part, which is why I borrowed theirs. So the facial landmarks, right? Ideally, if we had a camera pointed at a person as they said the sarcastic comment, so that there's full representation of all 68 points, that would be ideal. But that's not really practical in the real world. So there's actually some libraries out there, which I've used prior, that actually give you estimated three-dimensional points in three-dimensional space. So it'll actually give you X, Y, and Z coordinates. So that could probably be more accurate. And the one thing I didn't do that I did do for the acoustic portion is you could probably do the CNN, so the convolutional neural network, tie the word to the face as I'm saying it. And that would probably increase the accuracy of the facial landmark even more. You actually have a blueprint of it. You can probably lift it and put it into the other one. And so for the acoustics, you could probably remove the background noise. And for the text, to improve the text, I actually didn't use the text because I actually think that the text, right, kind of at the top of it, I said the two sentences, said the same exact thing. I think what the most important thing is how I said it, right? How I delivered that statement. So it's facial expression and acoustics. I completely disregarded what what the text actually was. But you might be able to improve it by taking the entire context of that conversation and then kind of taking the context and folding it in, and maybe that'll give you that improvement. So I kind of already warned you, don't put this into production. This is more like an academic exercise kind of a thing. And I think this clip is the best reason why this won't work.
On behalf of Amy, I'd like to thank the devil and all the dark lords who
Don't do the devil stuff.
gave her this award,
Do the devil stuff.
allowed her to feast on the flesh of the innocent.
Thanks, everybody.
So this is Aubrey Plaza receiving and accepting an award on behalf of the show for Parks and Rec. Now, what's really interesting is she's like, her persona's deadpan, which is no facial expression. Try to keep as monotone as you are. And when passing this through that classification, it's going to come out as normal. So just because you can build a machine learning model, even at like 80% accuracy, doesn't mean that it'll work every single time, right? And so this is kind of like the weird proof of that. So, workshop materials. So again, everything and you can go to just get my GitHub, it's just first, last name, 2025 AIDev Europe, all of the code, the data sets, the already trained models, so that you can just use this and play with this on your own. Like I said, it's not perfect. It's more of an academic study, right? Because I kind of like did a dive, springboard off of the original research paper. But you can test the facial sarcasm model, the acoustic model, and then do the multimodal inference. Oddly enough, like I said, one of the things I like to build medical models. I actually lifted all of that code and I used it to do Parkinson's detection using only the audio for someone with Parkinson's disease, just talking, and it is actually ridiculously accurate. And so in that particular case, I actually didn't go diving for a data set. Oddly enough, there's a data set that was already there. And what the original data set we were trying to do was they were trying to improve transcription, the transcription service, and they were using the Parkinson's data set in order to improve their transcription service. So I just lifted their data set to do Parkinson's analysis or classification based on pure audio. So like I said, I like to do cool, fun things, but all the materials are in my GitHub. You can go do all of this on your own. If you don't have an H100, you don't need any special equipment. You can do it on your laptop. And that is it. So I promise we're getting 15 minutes early, but there's 15 minutes of questions. I will answer any questions anyone has.
Bit of a weird question. Could
Yeah.
you repurpose this like for a light detector or something?
For what?
A light detector.
That's a very interesting use case. And I don't know. I think, so you're talking about trying to do voice stress analysis for lying?
Yeah, like visual cues.
Give it a try, right? Collecting the data is always the hardest part. Like you have to have data for someone saying the truth and then someone saying a lie, and you need to have a lot of it. So that's a very interesting use case, but that would capture what the person's saying and the intonation with it. So, yeah. Any other questions?
Have you tried to let both models speak to each other and correct each other?
Sorry, repeat that again. Oh, I forgot to repeat the question.
Have you ever tried to let the models speak with each other and correct each other? Like in case if there is, for example, there is no facials and the facial is not recognizing the sarcasm, then the audio mentioned that and then double check and this kind of.
Yeah, so I kind of glossed over the multimodal part. There's different ways you can combine both scores. So there's like one method, which is basically take the one with the highest confidence and just go with that one. And we did like an average. There's other ones where there's like 6 or 7 of them that I had calculated. And if you actually go into the code, where is the predict? There we go. So actually, if you go into the code, well, that's too large. There we go. So these are the different options that I had calculated. So you can pick, take a look at which one fits best for your particular 2 models that you want to put together. Like I said, like the one is a simple one. Whoever has the highest confidence, just go with that one. We actually did all of them, but in general, what I noticed when I was taking the audio and the facial landmarks, the average one works just as good as the other ones, but that seemed to give me kind of like the most consistent result.
Something comes to my mind as a suggestion for improvement, especially for the last video which you shared and it wasn't recognizing the sarcasm, is when there's a laughter or some kind of funny audio in the music or something in the video, then it can go back and even like you can get some speech recognition and double check the text and see if there is any sarcasm in the text, for example, or in actual voice. I think there's a lot to improve, and it was fascinating what you've done so far. But
so the text portion it actually does do.
Yeah. Okay.
So it actually, if you have enough data, it will actually compare the way every person says the word the. Oh. Right. Okay. And if there isn't, because we're actually tying the acoustics to the word, all the other stuff actually really doesn't matter. Like the spacing between the words, right? Because they're not saying anything. So that already happens for the intonation.
Thank you.
But yeah, but you're right. Like the laughter, if we just cleaned up a lot of that stuff, like remove the laughter, remove the music. But that's one reason why I said we need to pin it to something. So we pinned it to like the word, the transcription.
Okay, thanks.
Have you...
The mic, please.
Have you tried reversing this so that you give it text and then say produce a facial or set of facial expressions and audio that say this text in a sarcastic way?
I have not. That's very interesting. There could be many interesting use cases for it.
But the same data set would?
Yeah, I mean, you're talking about like fabricating like the facial expression and the acoustics with fabricated data. Yeah, I mean, you could like create like fake people to like do sarcastic and non-sarcastic statements. But yeah, I haven't played around with that. I've only done, the reverse of that. Like,
Oh, I think in your talk, you mentioned that you grouped the video in the roughly same length. I was wondering if you can explain why the length matters in your training. And I think you also mentioned you added some blank to make them the same length. And will that maybe influence the model, or it doesn't matter?
So if you say a sentence, and whether it's sarcastic or not, that sentence is going to be either long or it's going to be short. And when you're doing any kind of classification, you have to compare like to like things. So if you're going to compare this short sentence to this long one, it's very difficult to compare those things because this one takes 10, 15 seconds longer than this one. So like, how do you then compare those two things? And so the easiest way of like not trying, and there are ways of doing it. So what you can do is you can take the short sentence and pad with zeros so that you can actually compare to the long, the long utterance. I don't think that's probably going to yield good results because like I'm basically forcing it to like be comparable. But if you group things like in buckets, like any word or any sarcastic or non-sarcastic sentence that's 10 to 15 seconds long, let's put them in this bucket. And then if they're 10 seconds, we'll pad it up to 15, but that's more of a like-to-like comparison than comparing a 1 second to a 30-second clip, right? So then the next bucket would be like 5 seconds to 10 seconds. The next bucket might be for 0 seconds to 5 seconds. So that if I do inference on a 3-second clip, I'm going to compare that 3-second clip to all of the things that are in the 0 to 5 second bucket.
And you also notice like the prediction accuracy that tend to be more accurate for the longer clip? Is that a...
That's a great question. I don't know. I would assume probably. Yeah. Yep.
So,
Did you
Oh, go ahead.
Oh. It's actually a follow-up. So you split the samples into length buckets, right?
And that was only for the facial.
Yeah.
Yeah.
And do you try to ensure that there is like an equal, like a I don't know if equal, but like, you know, some kind of comparable distribution between sarcastic and non-sarcastic
Always.
clips
Yes.
in
Yeah.
each of the buckets separately?
Yes,
Okay.
I tried to.
Yeah.
It was their original data set.
Yeah.
There are some things that I threw out. So like as you were saying, there were actually some clips where there was no facial stuff, but there was audio. I still included that, but during when I actually, did the multimodal inference where I needed both, I obviously couldn't use that, but I still included it. And actually, one thing I did not mention is that the Sarcasmaholics data, like the sub data set of just that show, in my opinion, was super extremely problematic. And I ended up throwing out most of it. And it was kind of interesting because Golden Girls, Friends, and Big Bang Theory were all filmed in the United States. And they kind of all had like a weird film. Like it was like an expected formula for how the thing was filmed. But Sarcasmaholics Anonymous was filmed, I think, in the UK, right? And the way there was an extraordinary large number of clips, in my opinion, where there was people saying stuff but not actually on camera. And so I ended up throwing out a ton of that. Yep. Oh, sorry. Oh, yeah, you were, yeah.
yeah, okay, quickly. So I'm building something very similar for the healthcare system, which is related to low resource setting. Mm-hmm. So we are doing a lot of multimodal on top of it, right? It's not just look into like the people can, we are using PPG signals for video plethysmography to look into and see the vitals. And at the same time, it's a triaging software where it automatically tells that, there's a question and answer system. Mm-hmm. So what I really want to take away from this, is this a library where we can use it? Because one of the things which happens is like stammering and stuttering, mm-hmm. right? Now, these are conditions, but at the same time, when you do a triage, there could be the person is actually injured, or there is a jaw problem, or there is some problem. And the person is not actually stammering or stuttering. The person is actually going through a temporary problem. So if we can do that from an audio, because we're trying to do that on a multimodal, that we are not only looking into the audio part of it, but we're also looking into the imaging side and the mm-hmm. video side. And each of the frame is not only creating a signature of the image, as you're doing the same thing, image, you're taking a snapshot of the image. Mm-hmm. It is also taking the voice signature, and it is also taking the signature of the point at that instant, mm-hmm. what is exactly from all these attributes. And then we are putting it into a multimodal function.
Right.
Can we do a similar thing what you have done? Because this seems a little more straightforward than what we were thinking.
Yeah. So I mean, I like with any problem, there's 100,000 different ways of solving a problem. This is the way that I just happen to pick how to to solve it, to figure it out and try to solve and build a model that'll do both. It's not a library, and the reason why it kind of goes back to I conformed this workshop to the original criteria of that research paper. And so it's stuck in that frame. And like I said, our data set, the data set that I modified based on their original, so it's like a slightly smaller subset because I threw out some videos. It's small, and it's basically kind of like more, if you want to think about it, academic research. But kind of the takeaway from this is like start to finish, this is what a multimodal, this is how you do it. Yeah. And this is what the actual, because I don't think, like seriously, you don't see this stuff, and I don't know why. Like going from data pipeline, like how do I actually extract all this stuff, to actually doing the training, to actually doing the inference, and then putting two models together. And this is like hopefully like a cool, interesting and fun way of doing kind of that, like a workshop that'll get you start to finish. Yeah. Yep.
Yeah, I was thinking about, because I think you used mostly TV shows to do this, but this is like actors playing sarcasm. So I would like to know if we, I don't know, used a real person and a real conversation, would this actually work? Because I would assume it's a little bit exaggerated, especially the facial features.
100%.
And if you didn't include text, if that's what, yeah, okay. Maybe if you included text and used the context of a conversation, would this enhance the prediction rate?
I would, actually consider the text of like what they're saying, and then take in the entirety of the conversation to like aid with the text portion of it. I 100% would definitely improve it, in my opinion. But yeah, like you're saying, these are TV shows. It's exaggerated kind of like on purpose. In real life, like Aubrey Plaza, it's probably like, depending on the quality of your data set, you might get better results because it'll pick up those the subtle nuances, not the exaggerated nuances. So I think the theory is still sound, but you're right, those things are super exaggerated so that it's much easier to get a more positive result out of the models. But I think if you have maybe potentially a large enough sample set of everything with different kinds of flavors of how people do sarcasm, I think it might actually do fairly well, but the problem is where do I get the data set for?
Yeah, and also if, I don't know if there's like cultural differences to sarcasm.
Oh yeah, for sure. Yeah, like some people say certain cultures are dry, some are this or some are that. I would also argue, like kind of to your point, different accents, different, like how, even if you're speaking English, like you can probably tell from I don't know, people say Californians from the United States have a certain accent. That's where I'm from. So you could probably say that even accents would like throw in the weird mix of things. So you'd need samples from either what you're specifically targeting, or try to include the whole corpus of different accents in one language, like English. And then if you wanted to do it for like, French, you would probably need now a whole different subset for French, and now you start to see the data set problem. Yeah. Great question.
Thank you.
Okay, cool. Got 2 minutes, but I hope you enjoyed it. And yeah, you should be able to take all this home with you and try it on your own. So cool. Yeah.